Okay, this is the solution video for your midterm, plus the remaining part of the chapter 5, so that we can have a fresh start at next week, I hope. So let's start with problem number 1. So we are given with a flat universe with energy density that is scaling with a scale factor power of -5. And A is to get the time dependence of scale factor. So you start with calculating this, and you can integrate this out. And A should be proportional to time power of 2 over 5. Number B, obtain Hubble expansion rate at any given time and has to be expressed in terms of t only. So that's what you are with. By using the definition of Hubble expansion rate, you calculate this and you end up with 2 over 5t. Most of you got both of them right. And number 2 is also 10 points. Point out 2 facts of weakness of the Newtonian way to derive the Friedmann equation. Number 1, cosmological principle is violated because we assume a center, and there's no curvature term in it. It appeared with only a integration constant. So these are 2 problems that you are supposed to write. Problem set number 3, 10 points. You are looking at a photon from a galaxy today, and the scale factor when photon was emitted was 10 minus 2. The question is, how far is this galaxy away from in units of redshift? So it's very simple problem. You have this relation, 1 plus z is a as of today divided by a at the emission time. So z has to be 99. Okay. Problem number 4, it's also a numerical exercise. So we are given with a very early universe around redshift of 10 power of 10. A number 1 is 10 points, and temperature of the universe today is now 3K. And what was the approximate temperature at this redshift? 10 power of 10 minus 1. So what we've learned is that the temperature is inversely scaled with the scale factor. So the temperature should be 3 times 10 to the 10 Kelvin. And B, excuse me, 10 point. You are given with the Boltzmann constant to be approximate value of 9 times 10 to the minus 5 electron volt Kelvin minus 1. And you are asked to calculate the energy of a typical photon. I don't have the solution part, but it's K times simply temperature. So if you get it right, it's about 3 MeV. So I forgot to have the solution here. I'm gonna bring you the PDF as well when I load this, so it should be okay. And number 3, so the number C, 10 points. Question is, what's the elementary particles relativistic at the time? So it's 3 MeV. So gamma neutrino are surely relativistic, and electron mass is 0.5 MeV. So compared with 3 MeV, electron and positrons are supposed to be relativistic. Let's go to number 5. So galaxy is away from us by 2 times Hubble distance, and you're asked to calculate the speed, and it's a problem in terms of special relativity. If you naively calculate the velocity, you get 2 times speed of light, and it is not the speed of a given object, it's the expansion of the space, so it should be okay. Number 6 consists of 3 parts. So we are thinking of a cylindrically expanding universe as opposed to spherically expanding one that we discussed in our class. So we are given with this new coordinate, 2-dimensional, r and theta. A For a test mass at this location, you are asked to calculate the gravitational acceleration, and you have g and mu, this mass density per unit length along the z direction, r the distance, r units. You are supposed to use all of them, and we have this Gauss law for gravitational acceleration. This, so you get the this area times g, and you have I think I am missing mass somewhere, so mu times h, it should be the mass. So anyhow, there's a typo, but g, gravitational acceleration, should be 2g mu divided by r, and r unit with negative sign because it's attractive force. B, 5 point, you're supposed to calculate r double dot, and in terms of these parameters, and that's easy, so you can plug all that in. You'll get minus 2 pi g r I square normalized by r times rho I. Number C, let us define scale factor as this, and you are supposed to rewrite the differential equation for A, and you replace rho I to rho. So you do this, and rho t is basically rho I divided by A square. Therefore, A dot is gonna be minus 2 pi g A times rho, and most of you got it right, of course. Hopefully you had a good exam on midterm. And I'd like to briefly mention the remaining parts in chapter 5, so that we start with chapter 6 from next week. So I briefly mentioned the situation in matter, curvature, and lambda, and this is the Friedmann equation that you have to deal with. And first of all, if rho m0 is positive, rho lambda 0 is positive, then this guy, rho m0 plus rho gamma 0, is now greater than 1, so positively curved. And in this case, h square negative being unphysical, so there is no range of A to exist, so there's no Big Bang. So if you think about this second case, which is called loitering universe, and this is the very special case when some of these is very close to 0, and this means h is equal to 0 for a very long time. So if you take a look at this blue curve, and in some point of time, scale factor doesn't change, and instability comes in, and then it becomes larger. Sorry. And you have a situation where big crunch represent this curve. So universe expands, and it becomes the size of scale factor becomes 0. So it corresponds to big crunch when omega lambda 0 is negative. And for big chill is when omega lambda is 0.7. So big chill means when universe becomes expand and forever. Also, it's gonna be very cold. Nothing. It's, everything will be apart each other. And I explained this, and I'd like to show this plot where you have two-dimensional plane over lambda omega 0 and lambda m0. So depending on set of these two values, you have various situations. So it's a pretty busy plot. So this blue curve corresponds to two values of omega lambda 0 and omega m0, making loitering universe. Now above that becomes big bounce, below big chill. And this red dot, not dot, red dashed line shows two different ranges of curvature. Parameter kappa is +1 and below is -1, and so on. So you have to think a little bit to understand this plot, and so on. And getting this curve, loitering curve, is somewhat complicated, and if you really want to know how that is obtained, you have to, if you look at my lecture note, there's a reference explaining that. So if you are interested, you can go ahead. Now, the other topic is called radiation plus matter. So you are given with this Friedmann equation. And you can rearrange this all the way to this. H0 times dt is this. Now, this can be integrated analytically, or you can take a look at the integration table, or ask AI. And this is what you can get. And when A is very small, then you can get an approximation to this. Or if A is much greater than this A at the radiation matter equal error, then A is scaling with t power of 2 or 3 as opposed to t power of 1/2. So this is radiation dominant, and this is the matter dominant limit. And finally, I'd like to mention what we call benchmark model. So this is the closest universe that we have with us. So total radiation is 9 times 10 to minus 5. Total matter, 31%. And in it, we have normal matter component is slightly less than 5%. And 26% is the what we call dark matter. We know it's there, but we don't know what it is. And cosmological constant is close to 70%. And using this, you use Friedmann equation. Then you solve this Friedmann equation numerically. You cannot do it analytically in this case. And then you have this red curve from very early universe to today is right there. So it's right now the universe is expanding more and more rapidly, accelerated expansion, which is written in this formula, exponential kt, and this is matter dominant and radiation dominant. And this is written in log of ht, so that's how it was plotted. And from that, you can numerically get the scale factor at radiation and matter was equal. That's 10 to the minus 4. And if you convert that into time, this is 0.05 mega year. And the scale factor at matter is equal to dark energy is 77.77. So it's pretty recent. If you take a look, it's pretty recent. And time is 10.2 gigayear. Note that the age of the universe is 13.7 gigayear. Now A0 is equal to, as I said several times. Okay, thank you.